Well, hey there. We've got four little problems here that we want to finish up so that we're done with the problems in 6.1. Actually, it's two problems, but they each have an A and a B. So let's start tackling them here. The first is suppose that f is a function from A to B, g is a function from B to C. Show that if g of f is onto, then g is onto. And then after we're done, we'd like to show that the converse fails. The converse is if g is onto, then g of f is onto. Right? So, what we need to do to prove that g is onto is we need to take something out of C, just a generic, consider a general element C that's in C. Okay? And what I need to do is show that there is some kind of element in B that maps to that C. Okay? So, what we can do is think about g of f, right? G of f being onto, let's think about where that maps. G of f starts in A and it maps to C. So I'm guaranteed that in A somewhere, okay, there is an element that gives me C. So that's what we say. Since g of f is onto, then there exists some, remember that starts in A, so there's some little a in the set A such that g of f of that A gives me C. Okay? That's what onto means, is that if I've got something over here in my destination set and it's onto, then I've got to have something back over here that gets me that element. Okay? But now remember what composition means. If I'm able to take the composition of f and g composed with f of A and get C, that means there's some middle ground there, some element in the set B that lets me connect them, right? Then there exists some lowercase b in the set B such that, and two things happen. I get f of A gives me that B, and also g of that B gives me C. Okay? Which I now have established that for any C that I pick, I've got a B in the set B that gives me that C. Thus, G is onto the set C. Okay? All it took was me finding something that when I took G of that, I got the C, and there it is. Okay? Now, let's think about the converse. The converse says this: if G is onto, then G of f is onto. Okay? So is that true? Well, I don't think that it is, and let me perhaps pursue this with, we had a good example today from Jay Crafty, I think gave a good example, but I think I can do it with less elements. Let's just say that you got A and B and C, and they each have a 1 and a 2 in them. Okay, and I'm going to make sure that G is, so here's F will take things from A to B, and then G will take things from B to C. Well, I'll make sure that G is onto, so I'll probably just go straight across. Okay, and then where I think I could tear this up is to map everything here to the 1 or the 2, but leave something unassigned, right? So when I do this, I've got f of g of 1. Well, I did that completely backwards. Excuse me. Let me start that over. G of f of 1. Okay, well, f of 1 is 1, and then g of 1 is 1. And then g of f of 2, well, again, f of 2 goes to 1, 1 goes to 1, that's 1. So what's happening here is 2 is an element of the set C that has no pre-image in the set A. There's nothing in the set A that will give me a 2. Okay? Thus, G of F is not onto. Okay? So the converse will not hold. There's a counterexample to that. Okay? The B part of this says, all right, well, let's do a similar thing with 1-to-1. Okay? Here's F and G. F is from A to B, G is from B to C. Show that if the composition G of F is 1-to-1, then F inherits the 1-to-1. Now the one we did, we had stuff, so it's not mixed together. You know, we said if the composition is onto, then G was onto. That was the last one, right? Here what we're going to say is if G of F is 1-to-1, then the first one's 1-to-1. And then we'll show that the converse fails. But first let's prove that this works. Okay? Now what we'd like to show is that F is 1-to-1. So the way we do that is we say, all right, well, take a couple things where the function values are equal. Okay? So consider, and the domain of F is that's the set A. So consider A1 and A2 in the set A, such that F of A1 equals F of A2. Okay, now to prove that F is 1-to-1, I've got to show that A1 and A2 are the same number, or the same element. Not number, but the same element. Okay? Well, if these things are equal, see, we want to avail ourselves of this business right here. If these things are equal, then if I take G of each of those things, they would be equal because functions are assigned to each value is assigned to a unique value. So then G of F of A1 equals G of F of A2. Or we can say this with composition, G of F A1 equals G of F of A2. Okay? But G of F is 1-to-1. That means that these two things have to be equal. So I have actually proven now that F is 1-to-1. Here's something where these two, I plugged these two values into the function, they were equal, and I've proven that those two things have to be equal. Okay? Thus, F is 1-to-1. Or the other word we sometimes use is injective. Right? Okay. So that wasn't too hard to show. Now let's think about the converse. If F is 1-to-1, then G of F is 1 to 1. Well, again, I don't think this is true, and so let me go back to my example. 1 and 2, 1 and 2, 1 and 2, and I want F to be 1 to 1, so I'll just take them straight across. But I don't necessarily have to keep going straight across, right? I can map everything. I'll go to 2 this time just to be different. Right, everything in G could map to 2. So I've got, if I look at G of F of 1, well, F of 1 is 1, and that maps to 2. G of F of 2, well, F of 2 is 2, and then G of 2 is 2. So I've got these things equal, but 1 is not equal to 2, right? Those two things are not the same. So this is not 1 to 1. Okay? All right. 13 says, all right, suppose we got this function f from a to b, and we define an equivalence relation squiggle f on a by a is squiggle f related to b if their function values are the same. Okay. We want to show that squiggle f is an equivalence relation. Basically, we could think of this as, okay, partitioning all the things in, let's say we're doing a function over like the real numbers, so we've got a graph, and then taking all the points that are equal at a certain level, those are things in an equivalence class, and then move it down a little bit and you got a different level. All the things that are equal, the function values are equal at those points, would be another equivalence class. And so you can partition actually the whole set of real numbers for for a particular f. You can partition all those real numbers using this equivalence relation. All right, so to show it's an equivalence relation, we have to do 3 things, right? Let's tackle, oops, I meant to tackle reflexive first. Okay? So let A be something in A. Then A will most definitely be squiggle F related to A, since all we're saying is that the function value of each of these things is equal. Thus, squiggle F is reflexive. Okay. Now let's look at symmetric. Let's let A and B be things in A, such that A is squiggle F with B. Okay? What does that mean? Well, then that means that F of A equals F of B. Okay? But to get this turned around, I just need to turn that around, right? Then F of B equals F of A, which means then that I'm sorry, I'm doing it backwards now, that B is squiggle F with A. So I started A related to B, now I got B related to A. That means that thus squiggle F is symmetric. Okay? Alright, now let's tackle transitive. let A, B, and C be things in A such that A is squiggle F with B and B is squiggle F with C. Okay. Now what I need to show is that A is then going to be squiggle F to C, and I can just bypass the B. Okay. Well, okay, what does this all mean? Then this means that F of A equals F of B, and then this means that F of B is equal to F of C. Well, guess what? F of A and F of C both being equal to F of B, they're equal to each other. Then F of A is equal to F of C. And then that means then that A is squiggle F with C. Okay. Thus, squiggle F is transitive. Okay. All right. So that gives us the equivalence relation. That's our last statement. Therefore, squiggle F is an equivalence relation. Okay. Try and take this slow. Make sure it sinks in. Okay. You can always pause, but still. Okay. The last problem in this set then says, all right, fine. You've got this squiggle F relation defined by F of A equals F of B. We want to show that if this is the identity thing, that means that everything in the set is related to itself. Everything is related to itself. Okay? Then that happens if and only if F is injective or one-to-one. So we might want to assume this first. Okay? Assume that squiggle F is the inverse, no, not inverse, crud. Sorry, I'm getting ahead of myself. Is the identity relation on A. Identity just means that everything is related to itself. Okay, so assume that squiggle F is the identity relation on A, and now what we want to show is that F is one-to-one. Well, okay, suppose. How do we do this? Couple things where the function values are equal. Those there exist A1, A2 in A, such that F of A1 equals F of A2. Okay? Well, that means that these are squiggle F with each other. But because squiggle F is the identity relation, the only thing I have in there are things equal to themselves, related to themselves. So I know then that A2 has to be A1, or 1's 2, whichever. And that's all I needed to know that then F must be 1-to-1. Okay? Now let's go the other way. Now assume that F is 1-to-1. What I want to show is that every ordered pair that I have here is just mapping everything to itself, right? So consider two things that are equal. Not equal, I'm sorry, related. Consider A1 and A2 in A such that A1 is related to A2. And what does that mean? Well, it means that f of A1 equals f of A2. But f is 1 to 1. A1 equals A2. Okay? That means that every time I try this, I end up with things related just to themselves. And so, thus, squiggle f is the identity relation, or the identity function. No, I'm sorry, relation. I need to stick with relation, right? Okay? And that's it. That's all we had to do for that section. So what's left for us are 6 problems out of 6.2, which we will do on Thursday. And then I'll have a review session taped probably tonight, but maybe in the morning, that tells you kind of what's on the test and what problems you'll see similar stuff to. And then probably Thursday, right after the test, I'll get a accounting lecture going for you. Okay, that's it. Have fun, enjoy, and I will see you soon.